segments of spotlight talks, and we'll start with spotlights, and then in between there will be 2 oral sessions or oral presentations. So we will begin with a spotlight talk on dynamic network models from partial observations, and the presenter will be Elahe Galebi.
Hello, everyone. My name is Elahe Galebi, and I'm going to talk about this joint work with Bahar Mizar-Soleiman, Radu Gurisu, and Jure Leskovic. You may have heard of networks with wide-ranging applications, and they are often growing. For instance, new users join Twitter, and they follow each other. This adds new vertices and edges to the underlying network over time. There has been a lot of efforts modeling these dynamic networks. However, the efficacy of these models relies on obtaining full observations over the underlying network. But in real life, we cannot observe the whole structure. For example, social media companies are unwilling to share their topological structure due to privacy concerns and regulations. What's often known are the partial observations of the stochastic cascading process over the underlying network. A cascade is created by a contagion, such as a social media post, a virus, or a rumor that starts from some vertex of the network and then spreads like an epidemic from one vertex to another through the unobserved edges. For instance, epidemiologists can observe when a person gets sick, but they cannot tell who infected her. Therefore, the main question is, can evolving networks be inferred and modeled from these partial observations? We introduced difference, a generative probabilistic model that is able to identify the underlying time-varying network. What we do is that at step 1, we extract observations from the diffusion data. In each cascade, the first infection times of each vertex is observed. Any 2 vertices that have increasing infection time can introduce an edge. For example, at cascade 1, vertex D could have been infected through vertex A or E. E of C is the set of edges that could have been involved in the transmission. In the first round, we calculate the probability distribution over the edges of each set. We calculate the marginal probability of every edge in the set, and we sample Q edges from this marginal probability, and we add them to the set of observations. At step 2, we provide the extracted observations to the model and update their probabilities using a collapse Gibbs sampler. Here we use the model of mixture of Dirichlet network distributions to model the edges. For the next round, we get the updated probabilities for every possible edge in the network. We repeat the calculation of the probability distributions of each edge in the sets, and we sample again Q edges from these marginal probabilities of every edge. Then we update the model with the new set of observations, and we iteratively repeat the rounds until it converges. For the online inference setting, we discretize the time into equal time intervals. At each time interval, we only consider the infection times of vertices at that time interval, and we update the model using the observations in current interval. This way, we make sure that the edges that have been recently observed get higher probability. We applied difference to several synthetic and real-world data sets. For one, we used the data set of the European countries' financial transactions for the task of dynamic bankruptcy prediction, since the crisis hit the network at 2010. We used the window of length 2 years to build the cascade between bankrupted companies, and we predict the companies that are going to get bankrupted the next year. It can be seen that difference has a very good performance for the task of dynamic prediction. To sum up, our algorithm has the ability of identifying the underlying time-varying community structure, together with obtaining dynamic predictive distribution to use for multiple prediction tasks, such as diffusion prediction, extracting most influential users, and bankruptcy prediction. For more information, please come to our poster today. Thank you very much.
Okay, next up we have Sandian Ze presenting on, next slide. Are you sure? Presenting on stochastic non-parametric event tensor decomposition.
Good afternoon, everyone. My name is Sandian Zhe. I'm assistant professor at School of Computing, University of Utah. My research focuses on probabilistic machine learning. So our work is stochastic non-parametric event tensor decomposition. So first, what are tensors? Tensors are a type of very widely used high-order data structures that can represent interactions among multiple objects or entities, such as in collaborative filtering, online advertising, brain imaging, social interactions, and etc. So a fundamental framework to analyze tensor data is called tensor decomposition, where we organize those interactions into a tensor. And we introduce a set of latent factors to represent each entity from each tensor mode and learn a mapping from the latent factors to the observed entry values. So traditional decomposition approaches assume this mapping is multilinear, such as Tucker CP decompositions, which of course are very elegant and convenient, but they're insufficient to capture more complex nonlinear interactive relationships. Even more important, real applications usually include the timestamp information for those interactions. However, current decomposition approaches with those time information are really coarse. They either completely ignore the timestamp information, and then each entry is just store the number of interactions, that is the count tensor or frequency tensor. Or they abruptly discretize the time steps into rough time buckets, such as weeks, and then introduce extra time factors. They at most introduce some Markov assumption to encourage smooth transitions between the time factors. However, all those methods fail to capture the abundant fine-grained temporal dependencies between the interactions. So to address these problems, we propose our non-parametric event tensor decomposition. We first formulate a new type of tensor called event tensor, where each entry is not a numerical scalar. Instead, it consists of a sequence of interaction events. In this way, we preserve the complete time information. And then to decompose the event tensor, we hybridize Gaussian processes and Hawkes processes. So the latent Gaussian processes are used to model the background rate so as to capture the complex nonlinear interactive relationships statistically. And the latent Hawkes processes are used to model the fine-grained temporal dependencies among those interactions within or across different tensor entries. By hybridizing the two types of processes together, our latent factors will encode both the static interactive relationships and the temporal triggering effects. However, the exact inference of our model is intractable. So to address this problem, we further combine the sparse variational Gaussian processes and Poisson process superposition theorem to derive a fully decomposable variational model evidence lower bound. Based on that, we derive our doubly stochastic variational EM algorithm. So if you're interested in our work, welcome to our poster at 5. Thank you.
Up next, we have Eitan Richardson presenting on GANs and GMMs.
Thank you. So I'm Eitan Richardson, presenting the work on GANs and GMMs by myself and my PhD supervisor, Yair Weiss at the Hebrew University. So GANs are, of course, very popular. They manage to generate images that are new images that are sharp and remarkably realistic from more and more complex data sets of natural images. Still, it is not clear how well they represent the entire data distribution, and their utility for different inference tasks is questionable. In this work, we wanted to compare GANs to a simple generative model, the Gaussian mixture model. We train, we believe for the first time, GMMs on datasets of full natural images and compare them to GANs in terms of how well they represent the entire data distribution, how sharp and realistic the images are, what you can actually do with the trained model, its utility, and the interpretability of the internal representation. Because of the high dimensionality, measuring how well a model represents the entire data distribution is challenging. To that end, we propose a simple binning-based two-sample test termed NDB. We show that it easily manages to differentiate between the unseen test sets to all samples generated by the different GANs we tested. In addition, it can point to specific cases of mode collapse in GANs. NDB has the advantage of not relying on a representation obtained from a deep neural network that was pre-trained for classification, which is by design invariant to different image properties. We then turn to training GMM on full images, which turns out to be not so simple, again because of the high dimensionality. With the aid of some optimization tricks, we managed to train a variant of GMM called mixture of factor analyzers on full images with training time that is linear with the data dimension. The samples generated by our model are diverse and realistic. We show that they better represent the entire data distribution. They do not mode collapse. However, they are not as sharp as GAN samples. The internal representation of the GMM is interpretable, and it's interesting to see what each component learns. Once trained, the GMM provides simple tractable expressions for different inference tasks, such as likelihood computation and image reconstruction. Finally, we wanted to try and understand why the samples generated by our GMM model are not as sharp as GAN-generated samples. To try and answer that question, we trained a GMM in an adversarial manner and got surprising results. So to summarize, we present NDB, a new evaluation method for high-dimensional generative model. We train a variant of GMM on full images and demonstrate its advantage. And finally, we present interesting insight about generating sharp images from a GMM. Code for GMM training and inference, as well as for NDB evaluation, is publicly available. So if you want to hear more, please visit our poster number 59. Thank you. Number 59. Thank you.
Okay, the last spotlight for this mini spotlight segment will be Alex Elemi presenting with a great paper title, Gilbo, One Metric to Measure Them All.
Hi, I'm actually Ian Fisher, not Alex Elemi. And yes, I'm here to present, to tell you about Gilbo, One Metric to Measure Them All. not surprisingly, this is joint work with Alex Salemi, and we're both at Google AI. So the problem we're tackling is that generative models are difficult to compare quantitatively across different model families. In particular, if you have some GAN that you've trained on a particular data set, how can you tell whether or not it's better or worse than another GAN on from the same data set, or a VAE even? But if you think about it carefully, you can notice that actually the probabilistic form of these generative models is the same for both GANs and VAEs. You have some prior over a latent variable z, and you have some decoder, p of x given z. So given that they have the same form, you could imagine that if we should be able to come up with metrics that take advantage of this equivalence. The particular approach that we take is to try to measure the mutual information between the observed variable x and the latent variable z. So on the first line, we just have the definition of the mutual information, but we can expand the joint distribution p of x comma z out as p of z, p of x given z, which again is just our generative model. And similarly, in the log ratio, we can expand p of x comma z as p of x, p of z given x, and simplify. And that leaves us with this posterior distribution p of z given x, which is unknown and assumed to be intractable. But we can just make a variational approximation to the posterior, call that e of z given x for the encoder distribution. And this gives us a lower bound on the mutual information between x and z, which we call the Gilbo, the generative information lower bound. So we can train our encoder distribution just by maximizing the Gilbo. And you maximize the Gilbo by taking samples from the generative model, which is to say that training the Gilbo has no dependence on the actual training data set that was used to train your GAN or your VAE. So we did some experiments on 4 different data sets: MNIST, Fashion MNIST, CFAR10, and Celeb A. And we looked at 3,200 different GANs and VAEs trained on these data sets. And we measured their Gilbos and their FID scores, which is, I think, the most popular way of comparing GANs right now. We'd like to particularly take a moment to thank the authors of Are GANs Created Equal, who let us use their previously trained models. Their paper is also being presented at this conference. So what makes a good Gilbo? Well, it shouldn't be too small, as it is for these GANs where the Gilbo is less than log the number of classes in the data set. It's clear that none of these GANs has figured out how to generate realistic MNIST digits. But it also shouldn't be too big. And so one way of thinking about what is too big would be comparing the Gilbo to the best reported negative log likelihood on your data set. In the case of MNIST, that's around 80 nats. And these GANs all have Gilbos greater than 80 nats, and you can see that they've basically learned just to generate noise images. Another interesting point, though, is right around log n. So if you have a generative model that has learned to perfectly memorize the training data set, then the mutual information between x and z for that model would be log n, log the number of training samples. So it's particularly interesting to see that all of the GANs with the best FID scores cluster at log n for MNIST. Does this mean that these GANs have memorized the training set? Well, we don't actually know, but it is very suspicious. So really, you want it somewhere in the middle, and it's interesting to qualitatively compare models that have the same GAN. For instance, all the VAEs are in a small cluster of Gilbos. They're in gray in the image on the right. And if you compare the sample quality of those of the VAE's image to GANs that have the similar Gilbo scores, I think you'll agree that the VAEs actually have much better sample quality. So that's interesting and somewhat surprising. So given this new metric, we might care about how good of a metric it actually is. We can analyze this metric in terms of things like its consistency, its reproducibility, and the tightness of the variational approximation. And you might also wonder about whether or not the mutual information is infinite. It isn't, and you can come ask us why at poster 57. So give it a try. We have some code, and thank you.
Okay, so while our next speaker bunch is set up, while I introduce you, so we have an oral presentation now. So we will have Ricky Chen presenting with work with co-authors Shui-Chun Lee, Roger Gross, and David Duveneau. And the paper will be is titled Isolating Sources of Disentanglement in Variational Autoencoders. And Ricky will take it once the computer is set up.
Hello, I'm Ricky. I'm here to talk about how variational autoencoders regularize their representations and how we can use this to obtain so-called disentangled representations. So let's start by talking about the term disentanglement. The definition of this term is quite up to debate and isn't well defined in general. In our work, our ultimate goal is to learn a representation that has a distinct meaning associated with each dimension, and where each dimension can be changed independently. For example, this model that was trained using our approach aligns the notion of glasses to a single axis, so that traversing along this axis controls the presence or transparency of glasses across all faces. Another dimension changes the orientation of the hair's bangs without changing their identity or any other features. The goal of this paper is to be able to learn such a representation in a completely unsupervised fashion. This line of work touches upon enforcing independence in a simple manner and has potential applications such as interpretable decision-making when such representations are used in end-to-end systems and generation of samples with controllable semantics and transfer learning. For learning representations, we use the variational autoencoder framework. An autoencoder simply takes the training dataset, encodes each sample as a lower dimensional embedding, and then ensures that encoding has enough information to reconstruct the original samples. A variational autoencoder views each part as a probability distribution and assigns a prior to the embedding. This can be equivalently seen as a regularization. This is typically motivated as performing variational inference, but a full understanding of the KL regularization term can still be perplexing. A recent algorithm for learning a disentangled representation called the beta VAE simply adds a heavy weight on this regularization term by using a value of beta that is greater than 1. Part of this work specifically looks into what effect this term has in the context of disentanglement. So here's our first contribution. Let's define a joint distribution over the data samples and latent variables under the encoder distribution Q. Here we take n to index an example in the training data set and focus purely on this empirical distribution. So P of n is simply 1 over the size of the training data set. Based on this joint distribution, we put our focus on the marginal Q of z as it aggregates over the entire training set. So for a factorized prior, we can decompose that regularization term we saw previously into 3 terms. The first term is the mutual information between the data and z under this joint distribution that we've defined. The existence of this particular term in the elbow was identified by Matt Hoffman and Matt Johnson in their elbow surgery paper. Now the second term is total correlation. This term is interesting because minimizing it induces an independence regularization on Q of z and becomes 0 if and only if Q of z is factorized. Despite its rather unfortunate name, it is a measure of dependence rather than simply of correlation. Finally, the third term is a dimension-wise KL that regularizes each dimension of z independently. Now, the beta VAE assigns a large penalty to the entire KL regularization term, evenly penalizing all 3 terms in this decomposition. However, minimizing mutual information seems counterintuitive for learning a representation, and this has been heavily discussed in existing works. We can also reason about the role of the prior. We see that the prior now only appears in the third term and acts as a regularization for the one-dimensional marginal distributions. Note that while any 1D distribution can be easily warped into any other 1D distribution, this is not necessarily an easy task for the encoder since Q of z is a large mixture distribution. What's interesting is instead of designing a prior, if what we care about is learning an independent representation, then we can choose any factorized prior and amplify just the independent regularization in isolation, hopefully without affecting the other terms too much. To this end, we would like to be able to stochastically estimate all three terms in this decomposition during training. The main difficulty lies in evaluating the log density of Q for any single sample Z. This is difficult because Q of Z is a mixture distribution defined on the full data set. If we try to naively estimate Q based on a mini batch of samples, then most samples of N will end up underestimating Q of Z because Q of Z given N is close to 0. Instead, if we take the N that was used to sample that particular Z, then we know that Q of Z given N should be of a high value. So if we can use the same mini batch that we used to sample Z, we should be able to get a more meaningful estimate of Q. To do this, inspired by importance sampling, we used a weighted average computed from the same mini batch to obtain an estimate for log Q. Note that a very similar estimator can be constructed for the one-dimensional marginals of Q as well. This estimator ultimately is biased, but we find that it still works well in practice. We note that some follow-up works have created slightly better estimators, which may work even better during evaluation. We can use the full data set to exactly compute log Q, so this estimator is used only during training. Okay, with this, we can now set arbitrary weights on the individual terms in our decomposition. This lets us isolate and amplify the different forms of regularization that were already present in the elbow objective, depending on what properties we want the model to have. In pseudocode, the standard elbow can be estimated like so. Instead, to obtain the terms in the decomposition, only a very simple modification is required to any standard elbow estimation code. The simplicity of this approach means that it can act as a drop-in replacement for any elbow-based algorithm. Once the terms are estimated, we can assign a large penalty to the total correlation to learn a factorized representation while keeping the other weights at 1. And we call this algorithm the TCVAE. Incidentally, this results in an equivalent objective to the factor VAE that was proposed by Kim and me last year at a NeurIPS workshop, although they use an additional discriminator network to estimate KL for training. In our case, not only do we not require any additional hyperparameters or neural networks, we can arbitrarily weight the other terms should the need arise. And we did try this in our ablation experiments. Okay, so now that we have an algorithm, how will we evaluate the success of a disentangling algorithm? Previous works have designed classifier-based metrics, but here we instead focus purely on statistical quantities. Note that this evaluation is only done to test and compare unsupervised disentangling algorithms and is not used for training. Suppose we have some ground truth factors V that we want the algorithm to recover. We can then define a joint distribution over the factors and latent variables, again using our encoder Q. Now, the most ideal representation is one in which each factor is only reflected in exactly one dimension of the latent variable. So we can use this joint distribution and estimate the mutual information between every factor and latent dimension. Then for each factor, we can sort the latent variables based on how much information they contain about that factor, and then simply take the difference between the top two values and then normalize this to be between 0 and 1. Essentially, this metric is high if there is exactly one dimension that corresponds to each factor, while all other dimensions are independent. This is the main motivation behind our disentanglement metric, MIG. As this is a statistical quantity, we can obtain an unbiased estimator using the full data set for evaluation. Furthermore, this metric can be generalized to discrete and structured latent distributions, since the only requirement is that the density is computable. All right, so we first did some quantitative experiments using synthetic data sets with some known ground truth factors. The first data set is these sprites from Mathy et al. This is a data set consisting of images of a single 2D object with known factors such as the position, scale, and orientation. The second data set is a collection of synthetic faces with different poses and lighting conditions. We begin by verifying our previous claim that penalizing only the total correlation should perform better than the beta VAE, which penalizes all terms in our decomposition. The black bars in these box plots show the median disentanglement score over 20 random initializations. Note that InfoGAN and factor VAE both use discriminator networks to approximate divergences, which can lead to some unstable behavior, especially when using fully connected architectures. Also of note is that the TC-VAE approximates the same objective as factor VAE, but we were able to achieve similar or better scores compared to a well-tuned factor VAE. In general, TC-VAE seems to be more stable than previous algorithms, which helps it achieve higher disentanglement scores more reliably under our metric. So as previously mentioned, the TC-VAE algorithm learns factorized representations. But does independence between latent factors lead to representations that correspond to these ground truth factors? Here we show the relationship between total correlation and our disentanglement metric. And we find empirically that both beta VAE and TC VAE, there's correlation between independence and disentanglement. It's interesting to see this relationship quantitatively. In this case, factorized representations recovered ground truth factors. This was one of the main motivations behind independent component analysis, which was a hot topic back before deep learning took the spotlight. We ran TC-VAE on face images of celebrities, letting it choose the number of important factors. Of the 17 factors that it used to explain the data, we found that 15 of them had clear interpretations. Here we visualize 4 test images as their representations are changed along axis-aligned trajectories. And for each dimension, we extrapolated well beyond the data distribution to emphasize each characteristic. So I'm just going to quickly scroll through these in the interest of time. Because the algorithm is completely unsupervised, it sometimes needs to be creative to find independent factors for describing the data. It found interesting factors such as the hue and smoldering looks. It also found latent axes that can be used to generate bald females or mustached females, which are rare cases in the data distribution. So what are the future directions? Well, we don't know what factors we should expect from an unsupervised algorithm. The answer may lie in the model's inductive bias. So if you want to reliably recover specific factors, you may require specific neural network architectures. Along the lines of reliability, can we build better stochastic estimators for enforcing specific properties in our representations? We don't think we fully characterize what disentanglement is. For instance, we haven't begun to address hierarchical notions of disentanglement. We've only proposed what we think is a clear and focused way to encourage a specific kind of disentanglement. So if you bought my notion on disentanglement, great. But there's actually a lot of existing work on this topic, each with a slightly different notion of disentanglement. So if you're interested in this direction, I encourage you to take a look. Finally, I would like to thank my collaborators, Shek-Chen Lee, Roger Gross, and my supervisor, David Duvenot. And thank you all.
So we have time for a couple questions, so why don't we start over there?
Hello. So your approach is fundamentally a likelihood-based approach in some sense, right? In that you're starting from a variational lower bound in likelihood and then modifying that bound. But one could imagine a very different style of learning algorithms for generative models, analogous to the algorithms that are commonly used for independent components analysis that you were alluding to earlier. And I wonder whether the whole community is really being misled in trying to get interpretability through likelihood-based approaches versus thinking through alternative estimators. Do you have any thoughts on that?
That's a very interesting question. I mean, like I said, so earlier, or much earlier, ICA, right, independent component analysis, still used probability distributions, but it wasn't really, it wasn't maximizing the output. It wasn't trying to maximize some sort of, it wasn't trying to, maximize some log density. So I definitely think, there are better ways to learn representations. It's just this is a fundamentally interesting way to think about them. Right? We have variational posterior, which is basically our representation of the data distribution. So I mean, non-VAE-based algorithms would definitely be interesting. It's just this is easier to analyze, at least for now.
Any other questions? Okay, if there's no more questions, we'll move on with the program. Thank you. Okay, so coming up, we have another round of spotlight presentations, and so the first spotlight, I'll get that in a second. The first spotlight will be Ray Lee presenting on sparse covariance modeling in high dimensions with Gaussian processes. Come on, Ray.
Hi, my name is Ray Lee. Here we propose a novel sparse covariance modeling method for high-dimensional representation. So a problem scenario is gene regulatory network inference. A gene regulatory network is a set of genes interacting with each other to control their expression levels. And to infer the network, we need microarray data measuring their expression levels in different experimental conditions. The challenge is that this is a high-dimensional problem. For organism, normally there's 10,000 genes, but their expressions are only measured in 100 experiments. Furthermore, there are regulatory relationships actually varying across experimental conditions. This is an example of 6 yeast genes, and there are regulatory interactions in different experimental conditions. So we propose to use Gaussian process to model the variations of the component relationship subject to the experimental conditions. And also, we use factor analysis to provide low-rank representation of the experiment-specific covariant matrices and the ARD prior to encode sparsity for the hub genes. So by introducing a latent variable z, the latent factor analysis provide a low-rank representation of the covariance matrices with loading matrix A of x. And we further factorize A of x to a coefficient matrix B and a matrix of basis functions U of x to control the number of bases we need to learn. And we put Gaussian process prior on the basis elements of the matrix U of x and ARD prior on the columns of the coefficient matrix to promote sparsity. For the experiment, for the GRN inference, here we have 3 organisms, E. coli, yeast, and Isoros. And here is our experiment-specific coefficient matrices performance in terms of interaction prediction, varying across different experiments. And if we set the median of the scores from the matrices as a threshold, we can plot the gene regulatory networks and successfully identify the hub genes. This is the overall performance comparison with 35 other inference methods. In particular, if you look at the down right, our method performs consistently better in terms of AUPR scores. Precision is more important in this problem scenario. And in another study, we implement our method to capture the temporal-spatial relationships between the crime rates from different census tracts in Washington, D.C. And in this scenario, the vectors are the crime rates in the 180 census tracts, and they are indexed by the weeks between 2016 to 2018. And here are the comparison of our estimated posterior mean and the posterior covariance compared to the data mean and covariance. And we also did the 1 week ahead prediction about the crime rate for each tract for the first 16 weeks in 2018. And this is the overall performance compared with our competing methods. So in summary, so our methods scale well to high-dimensional observations, and the inference involves sampling from n-dimensional Gaussian distribution. Okay, thank you.
Up next, we have Moinmir Mutni presenting on efficient high-dimensional Bayesian optimization with additivity and quadrature Fourier features.
Good afternoon, everybody. So I'll be talking about high-dimensional Bayesian optimization. This is a joint work with Andreas Krause from ETH Zurich. So we're interested in finding a global maximizer of a potentially nonlinear function g using only noisy zero-order oracle. We adopt a Bayesian perspective where we assume that the function g is sampled from a Gaussian process which encodes prior knowledge about the smoothness. We can also use equivalent frequentist assumption. If we associate a cost to evaluating a function at a suboptimal point and sum this cost along the whole optimization procedure, we can define a metric called cumulative regret. And we formulate an algorithm that tries to minimize this regret along the optimization procedure. The key challenge here is that you want to explore the function in unknown domains, but yet at the same time look in the domains where potentially a maximizer can be found. In order to solve this dilemma, we resort to the framework of Bayesian optimization, which defines a sequential decision problem where the next decision is based on a maximum of so-called utility functions, sometimes known as acquisition function. So the challenges of high dimensions are twofold. On one hand, they're statistical, which come from information theoretical considerations. And if we want an algorithm that's statistically efficient, we need further assumptions. The assumption that we make in this work is that the function that we are trying to optimize is additive, meaning that it decomposes into sum of functions where each of these functions depends only on a small subset of variables. Sometimes we even allow for overlap between these variable groups. And as a measure of complexity, we define so-called effective dimension, which is the size of the largest group. The computational challenges of high-dimensional optimization is the main focus of our work. On one hand, since we're using Gaussian processes, there is kernel inversion cost, which we significantly reduce. And secondly, optimization of this acquisition function can be sometimes as challenging as the original problem. We also simplify this to a simple coordinate optimization. To achieve these significant improvements, we make use of integral representation of kernels. We know that every stationary kernel can be represented as a Fourier transform. And this integral can be further approximating using a sum, which leads to inner product in a high-dimensional space, also known in literature as Fourier features approximation. A standard way to construct this finite sum approximation is to sample inducing frequencies according to a Fourier transform of a kernel. This is the motivation behind the celebrated work of random Fourier features. In this work, however, we use Gaussian quadrature. The Gaussian quadrature and our assumption of additivity causes that we have a favorable scaling with dimension, and our error on the approximation decreases exponentially with the size of the finite sum. To demonstrate the quality of this approximation, suppose that we are trying to optimize this function and we have these noisy point evaluations. If we fit our Gaussian posterior mean and confidence estimates, we see that it fits the data nicely and extends also to the unknown part of the domain. If we had used random Fourier features, we see that the unknown part of the domain, the posterior mean and confidence estimate would be completely off. With the smaller size of basis size, smaller finite sum approximation, we are able to completely recover the posterior mean and the confidence estimates using our approximation. So the main contribution of this paper is first, efficient and provably accurate high-dimensional Bayesian optimization using additive models. The ingredients which allow us to formulate this algorithm is firstly that quadrature Fourier features are provably better than random Fourier features for additive kernels. We are able to provide high-quality approximation and analytical form of posterior samples from a GP. With additive model, the Thompson sampling, which is a one form of acquisition function, popular acquisition functions, decomposes over the variable groups, over the additive variable groups, and leads to efficient optimization algorithm using just one pass of coordinate descent. And Thompson sampling is also no regret for squared exponential kernel. If you want to know more, please come to our poster 23. Thank you.
Okay, and here's some references. Okay, so next we have Zhi Wang presenting on regret bounds for meta Bayesian optimization with an unknown Gaussian process prior.
Thanks for the introduction. This is joint work with Bangjun Kim and our advisor, Leslie Cabling. So again, as a recap, Bayesian optimization is a popular global optimization approach when we have functions that are expensive to evaluate, and we only have access to potentially noisy evaluations of the function. Problems like this appear in many different areas. For example, action selection in robotics, hyperparameter tuning in machine learning, and so on. So a typical paradigm of Bayesian optimization is to model the function f with a Gaussian process prior, and then it sequentially choose the new query point, evaluate its function value, and update the model to be the posterior so that in the next iteration, the data collection strategy can be more informed. But in practice, we don't really have the full knowledge of what such a prior is. And a common workaround is to re-estimate the prior parameters once we collect more data on the function f. However, this introduces a Bayesian optimization version of the chicken and egg problem. So our prior model selection depends on the data that's been collected, and the data collection strategy depends on having the correct prior. Partly because of this, very little theoretical evidence can be shown when we don't have a known Gaussian process prior. In this work, we're going to break this circular dependency by instead letting the prior depend on some past experience with similar functions. So that means we're going to use them as the meta-training data, which means functions that are sampled from the same prior as the function f. Our approach can be viewed as a version of meta-training for Bayesian optimization, and it simply works in two phases. In the offline phase, we're going to collect those meta-training functions, which means functions that are sampled from the same prior. We use those data to estimate the prior, and in the online phase, we are given a new test function to optimize. We take the prior to model such a function, and once we have more observations, we construct unbiased estimators for the posterior and use them in a variant of the GPUCB approach. So here's how it proceeds. Basically, it chooses the input that has the highest upper confidence bound to evaluate in every iteration. One thing to notice is that our estimations of the posterior variance and the UCB coefficient both depend on the number of meta-training functions. So roughly speaking, those parameters are set in a way to compensate our uncertainty about our estimation. And the more meta-training functions we see in the offline phase, the more confident we are about our predictions. One nice thing about using these setups of the parameters is that we can derive a regret bound for meta Bayesian optimization, even if the Gaussian process prior is unknown. So here we show a version of the regret bound for the simple case where there's finite inputs and the underlying ground truth kernel is linear. In this case, the regret bound we care about is the simple regret, which is defined as the difference between the best function value and the function value of the best observation. Under the assumptions that our meta-training functions are indeed sampled from the same prior, and that we have enough number of those meta-training functions, we can show that if we have t number of observations on the test function, with high probability, the simple regret can be bounded by this expression with two multiplicative terms. The first term decreases to a constant as the difference between n and t increases, and the second term decreases to standard deviation of the observation noise as the number of observation t increases. For more general results, please come to our poster. Empirically, we verified our experiment. We verified our approach in robotics tests. And I'll see you at the poster. Thank you.
Great. Okay, so for the last spotlight of this group of spotlights, we have Ilya Bugonovich presenting about adversarially robust optimization with Gaussian processes.
Hello, everyone. This is a joint work with Jonathan Scarlett, Stephanie Gelka, and Volkan Jevher. In this talk, we look at the black box function optimization problem, where our goal is to optimize some unknown utility function f. No gradient information is available, and the only way we can learn about this function is through noisy and expensive point evaluations that are chosen sequentially. We focus on a popular approach to this problem, known as Bayesian optimization, which models the unknown function as a Gaussian process and allows us to encode the smoothness properties by suitably choosing the kernel function. This approach has proved to be very effective in practice, particularly in reducing the number of expensive function evaluations. In our paper, we look at the robust version of the previously explained problem. Our goal is to discover a design X star that maximizes the unknown function, but that is also robust with respect to the worst possible perturbation that we denote with delta. So in this setting, the final reported point by the algorithm might be perturbed by an adversary up to some maximal distance that we denote with epsilon. So the main motivation for studying this problem is that we seek to discover a design that is robust with respect to possible adversarial attacks, implementation errors, or any other source of perturbation. In this image, we illustrate the main difference between the robust and the non-robust problem. We show the original function that we sequentially query, and we also show the version of this function that is perturbed function version for some particular value of epsilon. So in this example, the design that corresponds to the global maximum of the original function is non-robust with respect to adversarial perturbation and is strictly suboptimal for our problem. On the other hand, a design that corresponds to the local wider maximum of the original function is both robust and the optimal solution to our problem. A great number of non-robust Bayesian optimization methods have been developed over time. We list some of them on this slide. In our paper, we developed a robust Bayesian optimization algorithm that we call StableOpt. We were inspired by the Gaussian process upper confidence bound that works in the non-robust setting. So at every round T, StableOpt computes model-based upper confidence bound of the unknown function. And then in the first step, it selects a point that is maximum optimal in terms of this score. In the second step, StableOpt tries to estimate the robustness of the previously picked point by looking at the worst possible perturbation for this point. Here we are being pessimistic in the face of uncertainty, meaning that we're using the lower confidence bound in order to find the worst possible perturbation. In the final step, StableOpt just observes the noisy function value at the perturbed point, updates the statistical model, and then this procedure repeats in rounds. Our main theorem states that if you use StableOpt to sequentially query the unknown function sufficiently many times, then we can report a point x capital T such that the perturbed function value of this point is at least the optimal perturbed value minus some target accuracy that we denote with eta. We can observe that the total number of points that we need to query, denoted with capital T, depends on the target accuracy that we want to achieve, but it also depends on the kernel-dependent information quantity denoted by gamma. So this theorem works for general kernels, but in our paper we also provide the kernel-specific bounds. So StableOpt and its theory can be easily extended to various different robust optimization settings. For example, robustness to unknown parameters. Here the goal is to choose parameter x that is robust with respect to different possible values that some other parameter theta can take. For example, when tuning hyperparameters, we might want to find hyperparameters that are robust with respect to different data types. One more interesting setting is the one of robust group identification. Here we assume that the input space is partitioned into groups, and our goal is to identify the group with the highest worst case function value. For example, in group movie recommendation, we would like to recommend a group of movies to a particular user such that every movie from within this group is up to the liking of the user. As I already mentioned, StableOpt and its theory easily extend to these and some other interesting robust optimization settings. So for more information on StableOpt and its variations, please come and visit our poster. Thank you.
So while the speaker sets up the laptop, so we'll have an oral presentation. So this is going to be work by Tal Friedman, who will be presenting the work, and Guy van den Broek. And the paper will be titled Approximate Knowledge Compilation by Online Collapse Importance Sampling. So is it working?
Okay, cool. All right, thanks for the introduction. I'm Tal, I'm a PhD student at UCLA, and this is work with my advisor, Guy van den Broek. So we're going to be talking about discrete probabilistic inference here. So a good starting point for this is to talk about factor graphs. So factor graphs are a powerful representation tool. They can represent, your Bayesian networks, your conditional random fields, your restricted Boltzmann machines, that kind of thing. And factor graphs are really nice because they give you kind of this visual graphical representation of the key features in a joint probability distribution, which is the independence properties, right? So, this factor graph is showing us that the probabilities of A and B depend on each other, that B and C depend on each other. But if we know the value of B, then now we know that A and C don't depend on each other anymore. So factor graphs are nice, but ultimately what we really want to be doing with a joint distribution is asking questions about it, right? And in general, this is hard. So, for example, if we wanted to know the marginal distribution of A summed over all these other variables, this is in general a very difficult problem, right? So if we wanted to do exact inference, so to compute these probabilities exactly, what we would typically do is we would use what's called knowledge compilation. We'd build kind of an arithmetic circuit representing the factor graph. You may have heard of like a binary decision diagram or a sum product network. And then once we have that circuit, they're what's called this like tractable form. So basically, this marginal and a whole bunch of other queries and manipulation operations, we get them kind of for free. And these circuits also have some kind of nice properties where when we're building them, we compact them by taking advantage of, kind of more subtle independence properties and sort of logical structure if it exists. But these circuits have kind of one problem, which is that they don't scale, right? We know just at a level, at a complexity level, we know that they're solving exactly a problem that's really hard. So we know that at some point we're just not going to be able to build this if you pick a factor graph large enough. So what we would like to do is we would like to take all of these benefits from knowledge compilation of having some exact inference, of taking advantage of these independence properties, but we'd like to also get kind of these nice benefits of doing sampling where it's scalable, it's anytime, it's, just give me as much time and resources as you can and I'll give you the best answer I can come up with. And what we'd really like is to kind of sit in the middle and take advantage of both of these things, right? Okay, so if we want to take advantage of some exact inference when we're doing sampling, the way that we typically do this is through something called collapsed sampling, or you may have heard it called Rao-Blackwell sampling. And the idea is that you do sampling on some of the variables, and then you do exact inference on the rest conditioned on that sample. So if we go back to our factor graph, maybe we decide that we're going to sample variables A and B, so we pick values for that. We observe those sampled values. And now we're going to compute exactly the probability of C given A and B. And we've made use of both. OK, so this is kind of a powerful variance reduction technique. And it's pretty useful. But there's this very difficult question that it raises, which is which variables do we sample? Which ones do we do exact inference on? And I'd kind of even push that one step further and ask, like, is it always possible to pick a correct set ahead of time, right? And I'm going to argue that the answer is no. And to kind of get an intuition for it, let's consider an example, right? So we have a network of people, and we're interested in whether or not those people smoke. And now we know that friendship has an influence on kind of, if you're friends with someone and they smoke, you're more likely to smoke. And we've decided ahead of time that we're going to sample these friendship variables. And now, two different samples that basically look like factor graphs, right? If you take each of these edges as being kind of pairwise factors, you have a factor graph. And now the problem is that if I want to pick from here which variable to sample, there aren't really good choices for variables that will work in either case, right? say I pick variable 1, in the example on the left, this is going to help us a lot because this is kind of a densely connected region, so it's going to make exact inference a lot easier. But in the example on the right, exact inference was already easy because this is a tree structure. And by sampling, really, all that we're doing is just introducing more noise. We didn't need to sample this. So what we'd really like to do is we'd like to do sort of an on-the-fly selection and say that, based on the result of sampling those previous variables, now we get to pick, right? So, in our previous example, we'd like to be able to choose which variables to sample once we know what the friendships are. And we call this online collapse sampling. And we have a theorem in our paper that shows that you'll still get an unbiased estimator doing this. OK, so we have this idea here. So what are the things, that we need to do to be able to actually implement one of these samplers? Like, how do we do it? So the first thing that we still need to do is to decide what and when to sample, right? We haven't solved that problem yet. We've just given us tools to make it possible for us to solve it. We need to decide how to sample, right? Because we can't assume in general that we can directly sample from the distribution of the variable. So typically what we do is something called importance sampling, where we say we're going to sample from a different distribution, call it the proposal. And then afterwards, we're going to correct for that to make sure that our estimate is still unbiased. And here, kind of the key is that the proposal needs to be fairly similar to the true distribution. But here, the problem is actually even harder because we need to have a proposal for any variable conditioned on any other variables because we don't know what order this is going to happen in. And finally, we need to be able to do exact inference, right? So before we saw that you need to be able to do exact inference on C conditioned on A and B. But now this is kind of taken a step further because we need to be able to do basically any combination. We don't know what we're going to wind up with at the end. OK, so I'm now going to introduce the way that we do all these things, that we implement our sampler in what we call collapsed compilation. So the idea here is that we can go back and forth between doing exact inference and sampling. In our exact inference phase, we basically use knowledge compilation. We incrementally build a circuit that represents the factor graph. We go kind of factor by factor. Whenever the circuit gets to be too big, we move to our sampling phase where we kind of pick variables to sample and then pick values for them. And whenever the circuit is, again, small enough, we go back to doing our exact inference. So we continue doing this until we've considered the entire factor graph. And now what comes out of it is a circuit representing the factor graph where some of the variables have been sampled. OK, so let's revisit those three questions and see how we're going to answer them. Right, so, well, what and when do we sample? So the when is chosen for us, right? We just kind of have to do it whenever the circuit is too big. And the what is, well, we're going to use a heuristic on the current circuit. And to give kind of some intuition for what you would want from your heuristic, if you have a variable that's kind of very densely connected to other variables, but it's not very strongly correlated in all of those connections, that's an example of a variable you really want to sample. That dense connection is going to make exact inference hard, but the weak correlation makes sampling really effective. And if you have the opposite situation, then that's an example of something you really don't want to be sampling. OK, the next question is, how do we sample? So remember we talked earlier about how we're going to do importance sampling, so we need a good proposal distribution. So whenever we need to sample a variable, right, we have a circuit containing that variable and also containing a whole bunch of other information. But remember what we talked about earlier, right? These circuits are a tractable form. So all of these queries are easy, right? So we already have the circuit. So let's just compute the marginal of the variable in the current circuit and just use that as our proposal distribution. It's highly effective, and we're getting it for free. And finally, there's the question of how do we do exact inference? And I mean, this follows in a pretty straightforward way, right? I said the result of doing this is a circuit with sampled variables. So just run whatever query you need to on that circuit that you have. We know that any joint can be computed efficiently and exactly. OK, so you've run this a few times, and now you have a bunch of circuits. And for each of these circuits, you have a weight, which is how much attention should you pay to each of these circuits. Alternatively, you can also think of it as how likely was this circuit to happen. And you put all of these together. On each of them, you can compute whatever query you want efficiently. And you use those together, and you can approximate whatever query you want. So to validate this empirically, we basically study exactly the problem that we've been talking about, which is how do you compute a marginal in a factor graph? We're going to compare to a couple of other methods which use sort of this combination of exact and approximate inference, but in different ways. And to do this comparison, we're going to basically, at an algorithmic level, limit how much exact inference we're doing so that we can have sort of a better comparison of how they're using it. So we find that basically pretty much across the board, but depending on exactly which configuration of example and heuristic you're using, you get results that are basically either comparable to or slightly better than the state of the art. Okay, so I'm about to wrap up here, but my kind of 30-second takeaway for if you dozed off at the beginning and you want to know what you should remember is that we have these tools for doing exact inference from knowledge compilation that are very powerful, that take advantage of a lot of nice properties, but we know that they don't scale. And we have also these properties from our kind of normal toolkit of samplers, which let us sort of do the best that we can. And what we've presented today is a way of combining these and taking the best of both worlds to be able to still take advantage of all these same properties while also scaling. Thanks.
So we have time for a couple questions. So I have one question. So what is the intuition for like the type of graph that will screw up your method the most? Like, is there something that would cause it to only stay in the sampling stage and never jump to the exact inference stage?
So a very densely connected graph will cause it to spend a lot of time on sampling.
Okay.
If you pick the right type of heuristic for that graph, you can still do very well because you are a sampler. And one of those example benchmarks is basically a completely connected bipartite graph.
Yeah.
But yeah, it does depend a lot on the combination of how the graph looks and what heuristic you're picking. Yeah.
Great. Thanks. Any other questions? Please.
So you talked about sampling using a distribution from the circuit you've constructed so far.
Mm-hmm.
What about all the variables that you haven't added to the circuit yet? Don't they influence the marginal?
Yeah, they can influence the marginal, and it's not the exact marginal distribution for that variable. It's just in general, we found that it's a very good approximation, especially once you get kind of a little further into the process. So at the beginning, it can kind of struggle sometimes, which, one way to kind of improve this is to take a baseline proposal distribution that you can use at the beginning. But once you get sort of further into the sampling procedure and you've considered a lot of variables, we found that that proposal is actually pretty good.
Oh, so there's a proposal, and then but the importance weighting you do need in order to get the right answer in the end. You do need the influence of all those other variables?
Yeah, so when you compute the importance weight, you need to consider what you need the exact distribution, but of the combined proposal, not you only need a unnormalized version of the true distribution, and you get that at the end from the circuit that you have left.
Thanks.
Okay, let's thank the speaker. Oh, do you have a question? No. Okay, let's thank the speaker. All right, so we have one more round of spotlight talks, and we will open with Shun Zhen, who will present on DAGs with no tears, continuous optimization for structure learning.
All right, thank you. I'm Shun. This work is about Bayesian network structure learning using continuous optimization. So let's start with some basics. So we know graphical models are compact representations of joint distributions. And in the fully observable case, once we are given the graph, we can draw samples from the graphical model. And in this paper, we're interested in the inverse problem of sampling, which is structured learning. So we're given the data, and we try to estimate the graph that fits the data best. So let's talk about where we are in the literature. So there are two types of graphical models. One is undirected ones are called Markov networks, and directed ones are called Bayesian networks. And their literature shares same patterns. So first common method is called Bayesian constraint-based learning method, where you do a bunch of hypothesis tests to figure out the independent sets between variables, and then you construct the graph out of the independent sets. So, however, this method has some drawbacks, like it requires strong assumptions, such as faithfulness. And the second type of method is score-based learning, where you define a score function and you're optimizing your graph over this score, optimizing a score over this graph. And this can be further classified into two methods. One is local search, where you add or remove one edge at a time. And this has been done for both Markov networks and Bayesian networks. However, the very fact that we're doing local search is because we need to solve a combinatorial optimization problem using local heuristics. So about 10 years ago, a huge breakthrough happened in learning structure of Markov networks, led by methods like graphical lasso, and it has been hugely successful and widely applied in various fields like bioinformatics. So this method can be classified as score-based learning, but using global search, where you update all the graph parameters at once. So a natural question is whether you can do the same thing in Bayesian networks. But there are certain challenges in Bayesian networks. First of all, you have to deal with directed graph, which means you have to deal with non-symmetric matrices, and it's hard to deal with then symmetric matrices. And you also need to constrain your graph to be acyclic. So that's by nature a combinatorial constraint. So this paper is about taking the first step into addressing these challenges by converting a combinatorial optimization problem into a continuous one. So this is a one-slide summary of our paper. On the left, you're seeing the good old combinatorial score-based optimization problem, where we are maximizing over score and subject to the graph being a directed acyclic graph. And on the right is our equivalent formulation. We're changing the graph variable into a adjacency matrix variable, and we're replacing the graph directed acyclic graph constraint into a smooth function, smooth inequality constraint. And the right-hand side problem is now a smooth constraint optimization problem, and we can just use any existing numerical solvers to solve this. So our main contribution of this paper is show that such a function, h, exists. It's a smooth function, and it has a simple gradient. It can be easily implemented. It can be easily evaluated. And it can even measure how close to a DAG it is. So for the reason that it's so easy to implement, this method is called no tiers. And it can really be implemented in using like 50 lines of Python. And all we do in this piece of code is calling SciPy's LBFGS. And this code is on GitHub. Whereas in all the most of the existing algorithms, they require over 1,000 lines of code of very clever heuristics hand-coded. So let's look at some results. In this task, we're given the ground truth, where we have the ground truth graph, and then we're drawing samples from this ground truth graph, and we're trying to recover the graph structure. So on the left, you are seeing the heat map of the adjacency matrix of the ground truth graph, and in the middle, we're seeing our estimate. And you can see it's very close to the ground truth. On the right, we're seeing one of the baseline methods called fast greedy equivalent search, and that doesn't do very well compared to us. So one nice property of our method is that it's agnostic about the graph structure, so we can naturally deal with very different graph with very different degree distribution. So you can see on a scale-free graph, we have very different degree distribution, but we can still very closely estimate the ground truth, whereas the baseline doesn't do as well. So to summarize, we propose a novel smooth characterization of DAGs and use existing numerical solvers to solve this optimization problem. So we are building bridging between optimization and structured learning. So if you think the method, the paper is great, you should come to our poster, and I'll share with you some secret limitations. Thanks.
All right, up next we have Devran, sorry, what's your name? Bhattacharya, presenting proximal graphical event model.
Hi, thanks. I'm actually Dharmashankar Subramanian, and this is joint work with my colleagues Devaran Bhattacharya and Tian Gao from IBM Research. So the title of our poster is Proximal Graphical Event Models. And so what they are, I'll try to tell you that in the next few minutes. The object of study in our work is multivariate recurrent event data. And so notationally, it looks like what you see at the bottom. You have an event data set where each arrival epoch in this event data set has a label, and that label lives in some finite set, say M types of labels, and you have several such arrivals on a common timeline. And applications are numerous, clearly. The objective that we have here is to learn an interpretable causal structure that somehow models the joint dynamics or joint dependence across these event types. And so to that end, specifically, we propose a certain representation of such event data sets called the proximal graphical event model. So what is a PGEM? It's basically a graph where there is a node associated with each event type, of which there are finitely many event types presumed in the data set. And every node in this graph can be thought of as a stochastic process. It's a point process. And the meaning of the edges in this graph is the following. Being a stochastic process that has dependence on other processes, the dependence is in terms of the conditional intensity function. And the conditional intensity function here is sensitive or depends on a proximal, as in recent history, of the arrival epochs of the parent event types. So the model is specified in terms of a graph and a set of parameters. The parameters are these proximal windows that is associated with each parent in the context of any child under question. So in this example, for process A, which depends on itself, it only is sensitive to the arrivals of its own type in a proximal window of size WAA, as in an immediate recent history. So it's a bit like having memory in the system, and how much memory is it that matters for the current instantaneous arrival rate of any process under question. And so the model is specified in terms of the graph and a set of window parameters, and corresponding to any parental state. So since you are sensitive to the occurrence of at least one parent, and there are multiple parents, so you'll have different combinations. So if you have two parents, you can have none of them, one of them, the other of them, or both of them. So as such, there are combinatorially many intensity parameters that capture the instantaneous intensity or arrival rate. So as such, it is a piecewise constant history-dependent intensity model. And so what does it mean for learning in this problem? There are two things to learn here: the parameters of the model as well as the structure. So given that we have a model, it's a stochastic process model, and we have data, once the model is specified with some relatively straightforward algebra, you can write down the data likelihood per the stochastic model that we have proposed. And that's what it looks like in the slide. So the main two things that happen here are that the timeline the common timeline over which you observe all the multiple event data arrival epochs, it partitions into a finite number of parental states in the context of any child process under question. So the optimal log likelihood is one that optimizes this partition. So there are two quantities here that matter: the number of times that the child process is observed in any given parental state, and how long does that parental state last over the entire timeline. So optimizing it is easy when you have knowledge of the structure as well as the parameters. When you have knowledge of only the structure, you need more work to get the parameters. And finally, you need some work to search over all possible structures. So here are some example results on synthetic data sets. The model performs competitively or better than comparable other models. And to learn more about it, I invite you to come to our poster number 6, room 210, 230 AB. Thank you.
All right. So next we'll have Pablo Moreno Munoz presenting heterogeneous multi-output Gaussian process prediction.
Thank you. Well, this is joint work with Antonio Artés and Mauricio Álvarez. The problem that we deal with is when we observe pairs of input-output values where the inputs come from the real domain, but the outputs are a mix of continuous, binary, categorical, or discrete variables. This is what we know as the heterogeneous problem that is also a combination of different statistical data types. We want to jointly modeling this with Gaussian processes, but what we know is the majority of approaches for multiple outputs focus only on all regression or all classification tasks. That's the reason why we provide a novel extension of Gaussian processes for accepting any arbitrary combination of heterogeneous data. We find interesting applications, such as the medical scenario, where we can have a patient being monitored by several physiological metrics, such as heart rate or glucose level, each one belonging to a different nature. Also spatiotemporal analysis and even Bayesian optimization with multiple outputs. I begin by defining the heterogeneous likelihood in our model that we assume is a product of the different likelihoods, each one belonging to a different statistical data type. Each likelihood has its own parameters, and in the Gaussian process literature, this is usually assumed to be a nonlinear mapping of a function f that comes from a GP prior. For example, this function will be the sigmoid for the Bernoulli in binary classification, the exponential in the Poisson case, and the identity function for the mean parameter in the normal distribution. The question is, how do we jointly model these functions f? Well, what we assume is that all of them are a linear combination of a smaller set of latent functions u of q. Each one belongs to a different or independent GP prior, and implicitly what we are doing is imposing a multi-output GP prior with a coregionalization model of covariant matrix. We make all of this scalable by applying sparse approximations and variational inference. And our lower bound has interesting properties such as divergence that factorizes over the Q latent functions, and also the expectation that factorizes across samples. And of course, this is amenable for stochastic optimization. We use the variational version of the EM algorithm to fit both variational parameters and hyperparameters. Our results show improvements in multitask learning, where we are able of predicting in a binary classification task using information from a Gaussian regression 1. And of course, this is better than independent learning, and we demonstrate it in our experiments. Our model is also applied to large-scale datasets, such as the London house price data, where we combine binary classification and heteroscedastic Gaussian regression. What we saw is in that in the posterior curves, both tags share modes. Our code is publicly available on GitHub, and we present an easy syntax for defining any arbitrary combination of heterogeneous likelihoods. If you are interested, come to our poster, please. Thank you very much.
Okay, next we have Jeff Pleiss presenting GPyTorch, a black box matrix Gaussian process inference with GPU acceleration.
Hello, my name is Jeff Pleiss, and I will be talking about GPyTorch and black box matrix Gaussian process inference. This is joint work with my collaborators Jacob Gardner, David Bindel, Killian Weinberger, and Andrew Wilson at Cornell. So before I talk about Gaussian processes, I want to talk about deep learning and why it's so awesome to train neural networks today. Neural networks are really fast. They make really efficient use of modern computing hardware like GPUs. And this is especially true because a lot of the operations with neural networks essentially boil down to matrix multiplication, which is really efficient in parallel. Neural networks are really modular. When you're constructing a model, you're typically composing layers together in a building block style pattern. Typically, adding a layer takes a line of code. And the community has released a number of really awesome open source libraries that are really easy to use. And these three features make it really easy to rapidly prototype neural networks, and this is probably one of the reasons we see so much innovation in the field today. So now let's talk about Gaussian processes. GPs are fantastic models. They have a number of really compelling properties that make them very powerful. Unfortunately, being able to rapidly prototype with them isn't necessarily one of them. GPs can be a little bit slow. Even though there's been a lot of really awesome recent work that has scaled GPs up to really large data sets, when performing inference, you typically have to perform these really expensive operations on kernel matrices, such as log determinants and matrix solves. Typically, you would use the Cholesky factorization of these kernel matrices to compute these terms, and that's not an operation that can be efficiently parallelized on GPUs, so you don't really get the huge advantage of modern hardware. In addition, let's say you want to change your GP model by adding a multiple output, or maybe by using a scalable approximation. This could result in changing the entire inference scheme that you're using. You may have to rederive a whole new set of equations, and a small change in your model doesn't necessarily correspond to a small change in code. Typically, it corresponds to a large change in your code. So you don't have the same building block style pattern that you have with neural networks, and this makes it harder to rapid prototype. So that's what we set out to change in this paper. We want to make building Gaussian process models as fast and simple and easy as building deep learning models. And to accomplish this, my collaborators and I developed a new approach to Gaussian process inference, which we call black box matrix inference. This builds upon a lot of prior work that shows that a lot of the terms you need for Gaussian process inference can be derived through routines that use matrix vector multiplication with the kernel matrices. What we do in this paper is we introduce a modified version of the conjugate gradients algorithm that works in batch and computes all the terms you need for Gaussian process inference in parallel through some matrix multiplication routines with the kernel matrix. In addition, we introduce a novel preconditioner that's specifically designed for kernel matrices to rapidly accelerate the convergence of conjugate gradients. And in practice, what this means is computing the marginal log likelihood of a Gaussian process typically takes about 20 matrix multiplication calls with the kernel matrix. And this is really awesome for GPUs because matrix multiplication is probably one of the most GPU accelerated routines. There's another key advantage of this framework. So this can be easily extended to a lot of the more complex GP models that I was talking about simply by changing the matrix multiplication routine that you use with conjugate gradients. Scalable GP methods, multi-output GPs, and a lot of other models can be implemented simply by using a matrix multiplication routine that takes advantage of the structure that you have in the kernel. And this makes things really easy to implement, and it also is still fairly fast. This doesn't actually sacrifice any speed from any of these specialty inference algorithms, and it even reduces the computational complexity of the exact GPs to quadratic. We wrap this all up in an open source library, which we call GPyTorch, which is built on top of the PyTorch deep learning framework. And hopefully this video works, but I want to give you a demonstration just how fast this is. On the left, we have an exact Gaussian process training on 10,000 data points. And it does that in just a little bit over 2 seconds using BBMM and GPyTorch on a GPU. On the right, we have standard inference, which is also GPU accelerated. But what we find is that takes about 10 times as long. And we see similar speedups for a variety of these other GP models. So to summarize, if I can get to my final slide here, there we go. We're really excited about this because we think this is going to make it a lot easier and faster to play with GP models. Come see us at Poster 13 or check out GPyTorch if you want to explore. Thank you.
Okay, so that concludes this entire session. So go enjoy the posters. We saw a lot of spotlights, so go check out those posters and enjoy your evening.